So in chapter 25, problem number 39, we have a solid conducting sphere of radius r with the charge q on its surface. So what I've drawn here is the situation we're talking about, and we have this middle sphere has a charge of positive q spread along its surface. So there's our charge q. As we keep reading along in the problem, we can make sense out of what's going on. This central sphere is concentric with a larger, thick conducting spherical shell with inner radius r1, and we can see that I've drawn the inner radius of r1 here, an outer radius r2, and that there's a total net charge on this shell of negative q. So we have a negative q spread around on this outer shell. And we're asked to find the electrostatic potential in a few situations. We're asked to find the electrostatic potential, so that's going to be V in the case where R is greater than or equal to R2. We're asked to find V in the case where our R is greater than or equal to R1, but less than or equal to R2. And we're asked to find V when our radius is between big R and R1. And finally, part D, we are asked to find our V when R is less than or equal to big R. So we have these four situations that we have to solve for. And we're going to want to use the general equation V of R is equal to the negative integral of E dot dr plus V naught. We're going to integrate over some initial position, some position that we know, some zero position, to some final position. This is really the key to solving these kinds of problems, knowing that the potential is the integral of the electric field. So our task really is to find what the electric field is. What is E for all of these different situations, all of these different positions? So the first part, we need to find the potential when R is greater than or equal to R2. So we can draw a Gaussian surface because, as I mentioned, the key is going to be finding what the electric fields are in each of these situations. So we need to know what is the electric field for R is greater than or equal to R2. To find this, we can use the Gauss's law to figure out what this field is. So we draw a Gaussian surface with some radius r that is bigger than r2. So that's going to be my blue radius r. And if I look at this situation, I need to remember that I have a charge of plus q that's spread around on this inner sphere and a charge of negative q that's spread around throughout this outer conducting shell. And Gauss's law tells us that the integral of E dot dA is q inside of a surface divided by epsilon naught. Since I have a positive q and a negative q inside of this Gaussian surface, this blue Gaussian surface, that means that my E has to be 0 because the total charge enclosed is 0. So if E is 0, I can plug that into my equation for potential. So my potential is going to be equal to the negative integral from some reference point, some initial point, to some final point of E dot dr plus V at that initial reference point. And this is where this problem gets a little bit confusing potentially. Where am I integrating over? What is my initial position? And what is my final position? And what we really need to do is get used to the idea that we want to pick some initial position. We can pick any initial position, but we want to pick a convenient one. And for these kinds of situations, for a charge distribution like this, in general, the potential of a charge, V, is equal to K times Q over R. So we know that as we get to a really, really big radius, as R increases, the potential decreases. So if we go to R equal infinity, then our potential becomes 0. So this is a good reference point to choose. All the potential is 0 at infinity. So if we use infinity as our reference point, then this V initial, this V reference, becomes 0, and our potential is equal to the negative integral from infinity into our Gaussian surface, our position R, times E dot dr plus a 0. This gives us our V equation. We plug in our E equal to 0 and find that V for R greater than or equal to R2 is just equal to 0. I think part B is probably the trickiest part of this whole problem. So again, we have the same situation. We have a positive charge Q on the inner surface, and we have a negative charge, negative Q spread around on the outer shell. And we're asked what is the potential in between this shell, in the middle of this shell. So this Gaussian surface that we're going to draw to figure out our electric field is inside of this conducting shell. So we need to find E in between this shell, in the middle of this shell. And this requires us to remember a little bit of physics, specifically about what is the electric field inside of a conductor. We have a conducting shell. The electric field inside of a conductor is always equal to 0. Wherever your charges are, there's going to be an electric field that cancels from the opposite side. So let's say I have a little bit of negative charge up top. I am going to have an electric field that points from positive into negative. So I'm going to have a little bit of an electric field that points up. But then I also have a negative charge down at the bottom, and that field is going to point down. So at all points on this conductor, I have a field that might be going up. I'll also have another field that might be going down. So they're going to cancel at all points. We need to remember that the electric field in a conductor, and that's only inside of an actual conductor, is 0. That's what makes a conductor very, very useful. It's one of the properties that defines an object as a conductor. So E is 0, and we can do our integral again. We can do our V is equal to the negative integral from our reference point to some final point of E dot dr plus V at our reference point. And what we need to do here is we kind of need to break up this reference point because we're going to hit surfaces before we get to between our initial and our final position. If we're starting at infinity, I'm starting somewhere way far out here. Starting at infinity, and I'm integrating inwards. As I'm going inwards, the first surface I hit is going to be this R2. So I need to do, my potential is equal to the negative integral from infinity, the reference point that I've chosen, to R2 times E dot dr. My V0, because I chose infinity as my reference point, is 0, and I don't need to worry about that. But now I still need to take my integral in further. My Gaussian surface, my little r, exists inside of this R2. So I need to keep going, and I need to integrate from an initial position of R2 all the way into R of E dot dr. So this bears repeating what I'm doing again. I'm starting at a position infinity. My reference point is infinity, so that my initial potential, this V reference point, is equal to 0. And I'm integrating inwards to try to get to this surface R, this Gaussian surface that I've drawn. As I'm going inwards, I first hit this outer surface. This outer surface is at a radius R2. So that's going to be my final surface. But then I need to keep going inwards. I need to go from this second radius R2, from R2, into where my Gaussian surface is, which is my position R. So I need to integrate again from R2 to just regular old little r. Now my electric fields in both of these cases are both 0. We just figured the electric field out in part A for this situation was 0, and we just described that the electric field inside of a conductor is 0, and since this Gaussian surface is inside of my shell, I have a 0 potential as well, or a 0 electric field. Integrate over 0 and you get 0. So my potential in part B is going to be 0. Now in part C we have a new position. We have a Gaussian surface that's between our inner shell, our inner sphere, that has the radius big R, and our outer shell that has the inner radius of R1. So we're in this little Gaussian surface right here with this little radius R. So I need to find my electric field. What is my electric field for my R that is less than or equal to R, which is less than or equal to R1? So what is my electric field in this region? I'm going to use Gauss's law and find the integral of E dot dA is Q inside over epsilon naught. The charge that I'm enclosing in this case is going to be all the charge that's spread out around this sphere. That charge was equal to plus Q. So the charge enclosed is Q over epsilon naught, and that's equal to the integral of E dot dA. And the integral of E dot dA gives me E times 4 pi r squared, the surface area of my Gaussian surface, equal to Q over epsilon naught. And then I divide both sides by 4 pi r squared to find my electric field in this region is Q divided by 4 pi epsilon naught r squared. And I finally have an electric field that I'm going to actually have to plug in and integrate over. My equation again is potential is equal to the negative integral from some initial position to some final position of E dot dr plus V naught. I'm going to start at infinity again so that my reference potential is 0. So if I start at infinity, I'm going to need to integrate over multiple different endpoints. So I'm going to integrate from infinity, and as I come inwards from infinity, I hit this first surface. That first surface is R2, and get my E dot dr. And then I'm going to add on the integral as I go from R2 and integrate inwards. I'm going to hit my R1. So I have plus my negative integral from R2 to R1 of E dot dr. And then finally, I have my Gaussian surface that we're drawing in here again. This is the same Gaussian surface between my inner sphere and my shell. And I have my little r Gaussian surface. I go inwards from R1 to my little r. So we'll just write that integral in there, plus a negative integral from R1 to r of E dot dr. And since we've been solving this problem in steps, we already know that our first integral goes away to 0 from part A. Our second integral goes to 0 from part B, and we're left with just this final integral to solve, where our electric field, as we just solved using Gauss's law, is equal to Q divided by 4 pi epsilon naught r squared. So the integral we are left with solving is V equals the negative integral of from R1 to R of Q over 4 pi epsilon naught r squared. We can take our constants outside of this integral, and remember again that we're solving for this particular Gaussian surface that's between the sphere that's in the middle and the spherical shell. So we solve this potential. To solve this potential, we take the constants out of our integral. So we have our negative q over 4 pi epsilon naught, which all comes out of our integral, and we integrate over 1 over r squared times dr. From my endpoints r1 in our final point r. So we do this integral, and the integral of 1 over r squared is equal to negative 1 divided by r. And we need to evaluate this at our endpoints r1 and r. So we do v is equal to negative q over 4 pi epsilon naught. Our constants are still out there, and we evaluate at our endpoints. So we have negative 1 over r minus our initial position, negative 1 over r1, which becomes a plus. So this is our final answer for our potential. Negative q over 4 pi epsilon naught times negative 1 over r plus 1 over r1. And for our final position, we need to draw our Gaussian surface inside of this middle sphere. So here's our inside Gaussian surface inside of the middle sphere. There's our little radius r. We know that the electric field inside of this Gaussian surface, the electric field, if r is less than r, has to be equal to 0, because we're not enclosing any of the charge, because they tell us in the very first part of the problem that all of our charge plus q is distributed along the surface of this sphere. So we have no charge, and we can now find our potential. We can find our potential v is equal to the negative integral of E dot dl, or E dot dr, plus v naught. My v naught, my reference potential, was at infinity, so this is 0, and I need to bring my integrals all the way in from infinity. So my v is going to be equal to the negative integral from infinity to the first surface that I reach, r2, of E dot dr, plus the negative integral from r2 to r1 of E dot dr, plus the negative integral from r1, and now I'm going from r1 the negative integral from r1, and if I look at where I'm going from r1, this inner shell, all the way into this radius r of E dot dr, plus the negative integral from my total big radius of my inner sphere all the way in to my little Gaussian surface r of E dot dr. If I look at these, I know that my first integral is going to be equal to 0. That was from part A. Second integral is 0 from part B. Fourth integral from r to r has to be 0 because the electric field for r is less than big R is equal to 0. And I'm left with just this piece here from r1 to r. This is regarding the electric field that's in this region between the inner sphere and the outer shell. We already figured out what this electric field was. We figured that out in part C, so we need to plug that electric field in and evaluate it at these two endpoints. So we'll do that. I'm going to have that V is equal to the negative integral from r1 to r of my E, which was q over 4 pi epsilon naught r squared, which we found from Gauss's law, times dr. I pull out all my constants, and I get negative q over 4 pi epsilon naught times the integral from r1 to r of 1 over r squared dr. I do this integral, and the integral of 1 over r squared is negative 1 over r. So I have my negative q over 4 pi epsilon naught times negative 1 over r, evaluated at my endpoints r1 and r. And I plug in and evaluate this to get my v as negative q over 4 pi epsilon naught times negative 1 over the final position, final endpoint, minus a negative 1 over my initial endpoint. So those become pluses. And I get my final potential like so. And that's problem 25.39.